today's lecture we are beginning a new module. This module is on the widely used drift diffusion model. For this model we will be discussing the equations, boundary conditions, mobility and generation recombination mechanisms. So, we will discuss the formulae for these quantities. At the end of this module you should be able to write for the widely used drift diffusion transport model its 3 coupled equations in electron concentration n, hole concentration p and potential psi. You should be able to write the conditions imposed on n, p and psi at the contacted and non-contacted boundaries of the device to solve the coupled equations. Then you should be able to write the equations for field dependent mobility in bulk and inversion layers. And finally, you must also be able to write the equations for the different generation recombination mechanism. So, let us look at the organization of the equations from the previous module. So, you have the electromagnetic field equations feeding into the transport equations, the information about B, E and the force F on the electron due to B and E, and the transport equations yielding the current density of electrons and holes and the carrier concentrations of electrons and holes. Now, this information is fed into the electromagnetic field equations to get the solutions of B, E and F, and then the equations are solved subjected to some boundary conditions on E, B and heat flux Q at the boundaries of the device. Now, the drift diffusion equations which we arrived at in the previous module are repeated here. When we use the term drift diffusion model, it incorporates not only the equations of drift and diffusion current, but also all the other equations which are used together with this equation to derive the current and as a function of voltage for a device. Therefore, while the drift diffusion equations are only those which are shown here in blue color, the equations of the drift diffusion model would incorporate all the equations that are shown here, such as the Maxwell's equations under the quasi-static approximation and negligible magnetic field, and the carrier balance equation, and also the equation of heat flux. Similarly, we will also include equations for holes apart from the equations for electrons. Thus, you find that the drift diffusion model will consist of 2 of these equations, E equal to minus gradient of psi and divergence of epsilon E equal to rho, or del square psi equal to minus rho by epsilon. So, 2 of these equations, then carrier balance equation and drift diffusion equation for electrons as well as holes. So, that makes it 4 more, and then the equation for heat flux. So, you have 2 plus 4 plus 1, so the 7 equations in total. Now, very often we do not use the heat flux equation. Now, that leaves us with 6 equations. These 6 equations are shown here, and they have been organized into 2 sets. One set that we can call as flow creation equation, and another set that we can call as flow continuity equations. So, for instance, the equations of Jn, Jp and electric field shown in this column are referred to as creation because they talk about how the flow is created. For instance, equation for Jn here says that the electron current density is created by the diffusion and drift. Same is true for the hole current density here. And similarly, this equation tells you that the electric field E is created by a potential gradient. The continuity equations, on the other hand, talk about conservation of quantities during flow. The continuity equation for electrons is nothing but the carrier balance equation for electrons, and similarly the continuity equation for holes is a carrier balance equation for holes. And as we have already argued in the previous module, the equation of Gauss's law is also an equation of conservation of electric flux. Commonly, the equations of Jn and Jp involving the creation of these current densities and continuity of electron and hole concentrations are referred to as transport equations. Now, I would like to point out that the excess concentrations of electrons and holes are shown here using separate symbols, because in general a semiconductor may not be neutral. So, excess electron concentration at a point can be different from the excess hole concentration, though if you take the device as a whole it will be neutral, but at local points there can be space charge. So, the positive space charge at one point of the device may be compensated by negative space charge at other points to provide an overall neutrality. However, the generation rate of electron hole pairs G is the same in both these equations, okay, the hole continuity equation and the electron continuity equation. The set of equations related to the electric field are called electrostatic equations, because these equations are derived assuming that there is no time varying electric field and there is no time varying magnetic field. That is why these are referred to as static equations. So, electrostatics. You obtain the current voltage characteristics by integrating the current density J, which is nothing but the sum of the electron current density and hole current density. So, integrate the current density J over any contact area, ds is the contact area, then you get the current, and similarly you get the voltage across a device or potential between the 2 points, 2 terminals, by integrating the electric field from one contact to the other contact. So, dl is a line going from one contact to the other contact. Often the equations of Jn and Jp are referred to as current density equations, and those equations of carrier balance, the electron balance and the hole carrier balance, that is dou n by dou t and dou p by dou t, equations involving these are referred to as continuity equations. And this equation is the Gauss's law, divergence of E equal to rho by epsilon. Now, though we have 6 equations, ultimately they can be reduced to just 3. So, in a sense, actually in the drift diffusion model there are just 3 coupled equations, and these are continuity equations in n, p and psi. So, how do you get these? So, these equations are obtained by substituting the equations from the creation column into the continuity column and are subjected to conditions on n, p and psi at device boundaries. So, you take the equation for Jn from this column and put this equation for Jn here in the continuity equation in the divergence of Jn term. Now, Jn is given in terms of the carrier concentration and the electric field. The electric field in turn is dependent on the potential psi. So, if I combine this equation, the equation for Jn, and substitute it here, ultimately I will get an equation for n in terms of psi and other quantities. Same thing I can do for Jp. I take Jp and substitute it here in the whole continuity equation. And finally, I take this equation E minus grad psi and put it here in the Gauss's law. I get the Poisson's equation in psi. That is how I will reduce these 6 equations into just 3 coupled equations. So ultimately, I need to solve only these 3 coupled equations for getting the device current as a function of voltage, and that is what most of the simulators which are based on the drift diffusion model they do. Now, what is the physical meaning of mathematical coupling? So when we say these equations are coupled, the coupling denotes the fact that carriers perturb the field which causes their motion. So the motion of carriers is because of the field, but as the carriers move, they redistribute the concentration, and the redistribution of the concentration sets up a space charge, and this space charge creates an electric field according to the Gauss's law. So that is how it is a coupled situation. Now we have not written down the 3 coupled equations. I am leaving it to you as an assignment. Write the 3 coupled equations in n, p and psi, assuming that the mobilities of electrons and holes mu, the diffusion coefficients of electrons and holes d, the lifetime of minority carriers, and the dielectric constant of the semiconductor epsilon s are spatially invariant. Now in the previous module we had used the symbol epsilon for the dielectric constant of the semiconductor. In this module we are putting a suffix s because we will encounter a dielectric constant of the ambient, that is the surrounding of the device, and that we will denote as epsilon suffix a. To distinguish and to have clarity on which dielectric constant we are referring to, we are using a suffix s for the semiconductor dielectric constant. Let us look at the boundary conditions on n, p and psi. So the 3 boundary conditions, one each on n, p and psi, are required to solve the 3 equations. Now the boundary condition on a quantity such as n or p or psi can be on either the magnitude of the quantity. Now such a condition is called Dirichlet condition, or the derivative of the quantity. Such a condition is called the Neumann condition, or a combination of the other 2. So combination of the above 2 would be referred to as a mixed condition. In other words, we are saying the boundary condition can be on n, p and psi, or gradient of n, gradient of p and gradient of psi, or on a combination. So you can have a boundary condition on n on the electron concentration, which is given in terms of an equation which consists of both n as well as grad n, right. So that is the mixed condition. In general, the conditions on contacted and non-contacted boundaries are different. So here is a conceptual device showing the contacts and the non-contacted boundaries. Let us look at ideal boundary conditions on n, p and psi. This we shall illustrate with the help of an example. So let us say you have a uniform semiconductor block with a short contact on the top surface and a contact covering the entire bottom surface, okay, and you are applying a voltage between these two. This situation is referred to as a spreading resistance, right, because the current spreads from a smaller contact to a larger contact. Now at the contacts, the ideal conditions on n, p and psi are the carrier concentrations are uniform at their equilibrium values. So you see here n is equal to n naught, p is equal to p naught. So uniform concentration at this end wherever you have the contact. Similarly, you have uniform concentration equal to the equilibrium concentration at the bottom contact as well, n equal to n naught and p is equal to p naught. The potential is assumed to be uniform. So uniform potential like the uniform concentration. at the top contact the potential is assumed to be psi s equal to psi naught plus V. So, S here refers to the surface. Okay. So, psi s is nothing but the potential at the semiconductor surface. This is equal to a built in potential plus applied voltage. Since in general the semiconductor may be non uniform, there can be a built in potential. So, that is also incorporated here. So, V is the applied voltage. Now, as against this, the bottom surface, the potential is equal to the just the built in potential, because we are assuming that the applied voltage is 0. So, bottom is a reference. Now, what implications do these boundary conditions have? Let us for example draw the flow lines in the device which show the current flow. So, you find that the flow lines emanate perpendicular to the contact surface. So, here the flow line is perpendicular and here also the flow line is perpendicular. Current is flowing from top contact to bottom contact. Now, the fact that the flow line emanates or emerges perpendicular to the contact surface is because of the conditions that we have imposed. Since potential is uniform, the electric field at this surface can only be in the vertical direction or in the y direction. There can be no electric field in the x direction, because any electric field in the x direction would mean potential along the contact is not uniform. Similarly, since we have assumed that the carrier concentration is uniform, there can be no carrier concentration gradient in the x direction. Okay. So, any gradient has to be in the y direction. Therefore, even if there are diffusion currents in addition to drift currents, the sum total of these currents will be in the direction perpendicular to the surface. So, in the y direction only. So, that is how the boundary conditions have a bearing on the way the flow emerges from the contact or terminates into the contact. Let us look at the non-contact boundaries. Now, here you have a Neumann condition or the condition on the derivatives of the quantities. So, at the contact the conditions were Dirichlet, because they were on the values of the magnitudes of the quantities. For example, let us take this non-contact surface. What you are saying is that the potential gradient along the y direction, that is along vertical direction, is 0 at this boundary. This means no electric field either enters or leaves the surface normal to this surface. Similarly, no concentration gradient of electrons or holes can exist in the y direction, because that would mean electrons or holes are leaving the surface or entering the surface from outside. Similar conditions are imposed on the vertical walls as well. So, you can see that along this wall or this edge of the device you have no gradient in the x direction for either potential or carrier concentration. So, in this direction you have no gradient. So, no field can escape out of the device or come into the device. No current can go out of the device or into the device. Now, these boundary conditions in the non-contact will have a bearing on, for example, the potential lines. So, here we have drawn the equipotential lines. Now, you find that the potential line emerges perpendicular to the surface at the non-contact surface. Now, this is a direct result of imposition of the condition that dou psi by dou y is 0. So, there can only be dou psi by dou x. Same thing applies to the potential line emerging from the sides. So, even here the potential line is perpendicular. So, this means in this direction there is no field. Summarizing the boundary conditions, the ideal boundary conditions you have at an ideal ohmic contact, carrier concentration is equal to the equilibrium value and uniform, and the potential is also uniform at the applied voltage plus the built in voltage. At an ideal non-contact, the gradients of the concentrations N and P, which are perpendicular to the surface. So, the perpendicular sign here means perpendicular to the surface, and similarly the perpendicular gradient of the potential, all these are 0, because no current can escape or no field can escape out of the device or enter the device. Now, let us look at general boundary conditions. Now, what we have discussed so far are ideal conditions, okay, which may apply in many of the devices, particularly large size devices. Okay. However, as we shall find, there can be instances when you do not have the ideal conditions existing. Now, let us look at, in general, what are the factors that can influence the conditions on n, p and psi at the boundaries. We would like to define a few quantities here. JTE is thermionic emission current density, JTUN is tunneling current density, R suffix C is contact resistivity, rho suffix S is surface charge density. So, rho without suffix S is space charge, that is charge per unit volume, but rho suffix S is the charge per unit area. Psi S is the pinned value of surface potential. We have already used this term in the ideal boundary conditions. S is surface recombination velocity. Now, G suffix S is surface generation rate. Epsilon suffix A is ambient permittivity and epsilon suffix S is semiconductor permittivity. So, these epsilons include the permittivity of vacuum. So, the epsilon S, for example, would be equal to the dielectric constant of the semiconductor multiplied by the permittivity of free space. Now, we shall write the equations for n, and similar equations would be used for p. So, whenever we are writing equations involving both p and n, that will be evident. At any boundary at x equal to 0, let us assume that you have a semiconductor block as shown here, and we are assuming a one dimensional situation in the x dimension, and the boundary that we are talking about is at x is equal to 0. So, this vertical boundary. Now, at any boundary, the condition is imposed in terms of the perpendicular current density. This is the important point. Why? Because we can talk in terms of how much current is leaving the boundary or entering the boundary perpendicular to the boundary. At contacts, you will have a non-zero current leaving the boundary perpendicular to the boundary or entering the boundary. On the other hand, at non-contacts, you will have no current entering the boundary or leaving the boundary, right. Therefore, though ultimately we want conditions on n, p and psi, basically the conditions are on the current density, and from there we can derive the conditions on n, p and psi. Now, any current density, you know, is composed of the diffusion current and the drift current in our drift diffusion model. Let us explain the symbolism here. So, what does J n perpendicular 0 mean? What does what does perpendicular gradient of n at x equal to 0 mean, right, and so on. So, this equation interrelates the perpendicular current density at x equal to 0, the perpendicular gradient of carrier concentration, electron concentration at x equal to 0, the value of electron concentration at x equal to 0, and the perpendicular component of the electric field at 0, or the perpendicular gradient of the potential at x equal to 0. Let us explain this terms with the help of a figure. So, this is your semiconductor, and let us say this is the x direction and this is the origin. The current at this point in this direction is referred to as Jn perpendicular with a 0 there. So, this means the value of this current at this point. Similarly, the electric field perpendicular means the electric field in this direction at 0, that means the field here n of 0 means an electron concentration at this point. So, that would be n of 0. Now, what about the perpendicular gradient of n? So, for example, if within the device your carrier concentration of electrons is changing like this, then this is the gradient of the electron concentration, right, at the origin. So, this gradient is referred to as the perpendicular gradient of electrons, and since it is at this point, we are calling it as a suffix at x equal to 0. So, this is the meaning of the various terms which are used in the equation. At any non-contact boundary, again assuming that the boundary is at x equal to 0, the n and p are related based on the condition the total current J is equal to 0, that is Jn perpendicular 0 plus Jp perpendicular at x equal to 0 is equal to 0. Now, this is important. Actually, at a non-contact boundary, no current can enter, and when we talk about no current, you must consider the combination of electron and hole currents, right, not just individual currents. Let me give you an example where the individual currents of electrons and holes are non-zero, but their sum contributing to the total current is 0. Suppose I have surface recombination at this surface, okay, and this is your semiconductor. Then what will happen is the electrons will tend to move in this direction and holes will also tend to move in this direction, and here at the surface they will recombine. So, you see, because of the electron movement into the surface, you have an electron current. So, Jn, and that Jn is in this direction. If electrons are moving in this direction, your Jn perpendicular is like this, and if the holes are moving in this direction, it contributes to Jp perpendicular like this, and these two currents are cancelling each other, okay. That is how it is resulting in the condition J perpendicular at 0 is equal to 0, okay. So, this is an example where this is a non-contact surface with a surface recombination. You have both electron currents and hole currents at the surface, but sum total of them is 0. Therefore, at a non-contact surface, we must think in terms of the total current to begin with, and later on we may find that if there is no surface recombination, then individually also the currents can be 0. In most cases, though not always, following the conditions at ideal surfaces, we express the condition at a real contact in terms of n and a real non-contact in terms of the perpendicular gradient of n at the surface. So, we have said that under ideal conditions, an ideal contact, the electron concentration n equal to equilibrium value. Therefore, it makes sense to see under non-ideal conditions how much does n differ from n naught. Similarly, ideal condition at non-contact is in terms of gradient of n, the perpendicular gradient of n is equal to 0. It therefore makes sense to see how the perpendicular gradient of n differs from 0. Let us take some specific cases. Suppose we have a surface recombination velocity specified at the boundary x is equal to 0, then how would your conditions look like? specification of S sets this equation up. The perpendicular component of Jn at x is equal to 0 is equal to q times the surface recombination velocity into the electron concentration at 0 minus the equilibrium value of electron concentration at 0. So n0 minus n suffix 0, this term is the excess electron concentration at the boundary. So the current is proportional to the excess electron concentration. Therefore, you write the equation for Jn perpendicular including diffusion and drift, and this is the equation that is set up by the surface recombination velocity. Now this equation can be manipulated to express either n of 0, which is what will be the preferred equation at contact, or perpendicular gradient of the n at origin. So the manipulation will give, if you write n of 0, then it will turn out to be given by this formula. This is a very straightforward algebraic manipulation, so I am not working it out here. It is obtained from this formula. Now this is the formula preferred at a contact. Now note that you can recover the condition for the ideal contact by setting S tending to infinity. So in this formula, if you set S tending to infinity, you will get the electron concentration at boundary is equal to equilibrium concentration. Thus an ideal contact, ohmic contact, corresponds to infinite surface recombination velocity, if you want to specify in terms of the surface recombination velocity. Now you can manipulate the same equation, but now you try to express the perpendicular gradient of electrons. Now that is given by this formula, and this would be the preferred formula to use at non-contact to find out how much does this quantity differ from 0 for the ideal contact. Now you can recover the condition for the ideal contact, the ideal non-contact. So at the ideal non-contact, this quantity is 0. So we would like to see a real non-contact, how much does it differ from 0. So if you can recover the ideal conditions if you set S equal to 0 and the perpendicular electric field also equal to 0. So look at it here, if I set S equal to 0, this term drops off, and I will have to set perpendicular electric field also equal to 0 to get perpendicular gradient of n equal to 0. So you see, you need a combination of two conditions to define an ideal non-contact. Surface recombination velocity is 0 and the perpendicular electric field also is 0. Only then you will get the condition the gradient of the concentration perpendicular to the surface is 0. Suppose you choose to specify surface generation instead of surface recombination at x is equal to 0, then what would your formulae be? Now you are setting Jn perpendicular at x equal to 0 equal to minus q times Gs. Okay, this transforms to this equation when you split the perpendicular current density into diffusion and drift components. Now let us explain what is the meaning of this Jn perpendicular at x equal to 0 equal to minus q times Gs. So here we are assuming a surface generation at this end. Now surface generation, the unit is per centimeter square per second, number of photons impinging per centimeter square per second, and each of them, let us assume for simplicity, gives rise to an electron hole pair. So as a result of that, you have electrons flowing in, so you have generation of electrons and holes, and then the holes and electrons, they move in. So it is this current that we are relating to this Gs. Okay, that is what we are doing. Now you can again manipulate this equation as we did for surface recombination, and you will get these two equations, one in terms of the electron concentration at the boundary or in terms of the perpendicular gradient of electron concentration. So you will choose n of 0, this equation at contact and this equation at non-contact. Now if the thermionic emission or tunneling currents are specified at the boundary, then the equations look in fact very similar to the equations of GIS. So all that you need to do is that the above formulae apply with GS replaced by the thermionic emission current density plus the tunneling current density divided by Q. So you set GS equal to this value, then you get the boundary conditions in terms of these current densities. Now so far we have discussed the conditions on N and P. Now let us discuss the conditions on the potential psi. Now you would recall from the formulae that we derived for the boundary conditions on N and P that there was an electric field term also, the perpendicular component of the electric field at the boundary. This was entering into the formulae for the real boundary conditions. Therefore we need to understand how we can derive this information, that is perpendicular value of electric field, and we also need to know how the applied voltages and so on impose conditions. So this is what is done now. So general boundary conditions on psi. Now consider a contact with applied voltage V at the boundary x equal to 0. So we are applying a voltage at this end. Consequently the boundary condition on the potential at the surface of the semiconductor, so psi s is happening is inside the semiconductor at the surface. We will shortly explain this with a diagram. So this is equal to built-in voltage or built-in potential psi naught plus the applied voltage V minus the contact resistance RC into the perpendicular component of the current at the boundary. Now note that this current includes both electron as well as hole currents. So let us explain this formula with a diagram. So now this is the contact at this end and the voltage is applied at the outside, right, this is the voltage. Now the psi s is here. Now from this point to this point, when the current is entering the semiconductor and moving across the contact, it encounters a resistance. So if I were to expand this part, it is something like this. So this is psi s, this is V, this is the contact resistance RC, and you have a current. Now the current is in this direction and that is J perpendicular at the boundary. So this current, which is the same as this current, this is J perpendicular. So therefore you get the equation that V is equal to RC into J perpendicular at this point 0. So this is the x equal to 0 point. So you have this potential drop plus psi s. Right now I have ignored the built-in potential. Now carefully note the dimensions. The dimensions of RC is ohm centimeter square, because the dimension of this current density is ampere per centimeter square. So when you multiply these two, I must get volts. So I can transform this relation to express psi s. So psi s is equal to V minus this quantity, and then you can add the built-in potential. Now that is what is done here. Let us look at a non-contact. the non-contact again at the boundary x is equal to 0. So, here in general you may have an electric field entering the non-contact region and then leaving the surface. So, outside you can have an electric field as well as inside. So, that is why the relation between these two fields is expressed here. The field outside the device is in terms of the epsilon A, and the field inside the semiconductor is in terms of epsilon S, the term here, and rho S is a surface charge at the boundary. Let us explain this equation. So, this is the origin, and here you have a surface charge. This is Coulomb per centimeter square. The field at this point, but from outside, this field is referred to as the perpendicular field at 0 minus. So, 0 minus is this side and 0 plus is this side. Now, these lines will anyway continue through, and each of these positive charges will also contribute field lines, right. So, the field inside will be more than the field outside, assuming that the field is directed in this way, because this is our positive x direction, that is our convention. So, from here we can write the displacement epsilon A into perpendicular component of electric field at 0 minus, that is the displacement here, plus the contributions of the surface charge rho S. So, this displacement plus this will together contribute to the field inside. You can see there are more lines of field inside than outside, because each positive charge is contributing. Therefore, this is equal to epsilon S into E perpendicular 0 plus. So, 0 plus means field inside. So, that is how you get this relation. Now, you can convert this into a relation for perpendicular gradient of the potential by using this formula. So, this formula should be used for each of the electric fields. So, this one as well as this one. You can get then conditions on the potential. Now, at an ideal non-contact, this condition will correspond to no surface charge. So, rho S at that point 0 equal to 0, and the ambient dielectric constant is 0. So, when you say that no field escapes the device or no field enters the device from outside, you are indirectly assuming that the dielectric constant of the ambient is 0. Now, you know that this is evidently not correct. So, in general, for a device, field will always exist even outside the device volume. Okay? Now, this point has to be borne in mind. We shall shortly show an example where if you neglect this field in the ambient, you can get grossly inaccurate results. Now, before we go on to that example, let us make a point that the perpendicular component of the electric field in the semiconductor, so that is 0 plus. So, 0 plus is the semiconductor side of the boundary. Now, this electric field is needed to determine the carrier concentration at the boundary or the gradient of the carrier concentration in the real case, right. So, this we have seen in the formula that we derived. Now, this field will be required in the formula if your surface generation rate is non-zero or your surface recombination velocity lies between 0 and infinity. So, you are not having an ideal contact nor an ideal non-contact, and in addition the perpendicular component of the electric field is not 0. So, in that case you have to use this above results to get this perpendicular electric field and then derive the conditions on carrier concentration or their gradient. Another situation where you need the electric field information above is when you set the current density condition at boundary in terms of thermionic emission or tunneling. Now here is the example which tells you why you must consider the field in the ambient as well. Let me tell you the situation. This is a nanowire, a very small scale wire. So nanowire means the diameter of the wire can be of the order of say few tens of angstroms. That is the kind of wire that we are considering. Now this wire has been deposited on a substrate, and suppose you are measuring the current voltage characteristics of this wire by bringing in a probe in contact. So the experimental arrangement is shown here, and this is a simulation of this situation. Now as you can see, when you draw a diagram to scale, that a lot of field is going to exist in the ambient. For example, from the probe you will have field lines entering the semiconductor nanowire all along the surface. So because of the potential gradient, so this is 0.6 volts, top is 0.6 volts and bottom is 0. So there is a potential variation along the wire from top to bottom, and therefore there are field lines not only inside the semiconductor but outside the semiconductor, and they are entering the semiconductor. You can see that. Now these field lines will modulate the space charge inside, because after all the lines have to be terminate on some charge inside the nanowire. So therefore they are going to modulate the conditions of the charge and therefore the conductance of the wire. The blue lines here are equipotential lines. The field lines and the equipotential lines have been drawn based on the appropriate boundary conditions at the surfaces involved. For example, surface of this contact, surface of the nanowire, and also the surface of the substrate. Now what happens if you do not consider the field in the ambient? So you will set epsilon A equal to 0, then this entire field that is shown here will vanish and the field will exist only in the wire, right. Let me illustrate with a diagram. So this is your wire on a substrate, and this is your probe. Now if there is no field in the ambient, you have just a straightforward field picture like this. So this is 0.6 volts and this is 0. So you have field lines like this, but when you consider the field in the ambient, the field lines are emanating from here and terminating like this, right. So they emanate perpendicular to the surface here and terminate here. Now this contribute to charges. So for example, lines will terminate on electrons here. In other words, there will be enhancement of the negative charge in the wire. If it is an n-type wire, you will have more electrons, the conductivity will increase, it will be modulated. So that is the effect of the ambient field. Now that conductivity modulation you are going to ignore if you remove this ambient dielectric constant, and the effect is shown here. The simulated results, if you put epsilon A equal to 0, you get this current as a function of voltage, and if you put epsilon A equal to 1 as it is, because you have air outside, then you get this blue line, and as you can see the blue line passes through the measured data very nicely. Whereas if you did a simulation setting epsilon A equal to 0, you would get the red line which is grossly inaccurate as compared to the real condition. So this should explain to you why the boundary conditions should be appropriately imposed to get the correct results, and in particular one must be careful while neglecting the electric field in the ambient. So ideal boundary conditions should be used with lot of care. While they simplify your modeling problem and calculations, they may give you grossly inaccurate results, particularly for small devices. So we are towards the end of the lecture. A couple of assignments related to the boundary conditions. A hypothetical device simulator does not have the provision of setting surface recombination velocity S as a boundary condition. Explain how you could use the volume recombination model that is the recombination rate equal to excess carrier concentration by lifetime. This is the model of volume recombination. So, how you can use the volume recombination model of the simulator to simulate a value of S equal to 200 centimeters per second at a certain boundary of a device. So, you actually want to simulate surface recombination at a boundary, but your simulator does not have a provision for that. So, can you use a model for the volume recombination around this surface and simulate the surface recombination? That is the question. Another one, explain how S imposes a condition on N if the boundary is conducting, that is contacted, but on perpendicular gradient of N if the boundary is insulating, that is non contacted or free. Write an expression for perpendicular gradient of carrier concentration at an insulating boundary in terms of the surface charge S and epsilon A. So, assume surface recombination is present, surface charge is present, and the ambient dielectric constant is also there. So, the field in the ambient also has to be considered. Take all this into account and write an expression. Explain which of the quantities N, P, psi or their derivatives at a contact boundary are affected by the surface charge. Now, with that we have come to the end of the lecture. So, let us make a summary of the important points. So, in this lecture we began a detailed discussion of the drift diffusion model involving the drift diffusion current equation and other equations such as the continuity equations or carrier balance equations, the heat flux equation and the Gauss's law and an equation for electric field in terms of the potential gradient. Now, if you leave out the expression for the heat flux, you have 6 equations in the drift diffusion model, and we showed that these 6 equations can be reduced to just 3 equations in terms of N, P and psi, and therefore to solve these equations you need 3 boundary conditions, one on N, one on P and one on psi. Now, we explained how the boundary conditions can be imposed either on the value of the quantity or on the gradient of the quantity time on the derivative of the quantity. So, we discussed about ideal boundary conditions and real boundary conditions. The ideal boundary conditions were that the carrier concentrations and the potential are uniform at a contacted boundary, the carrier concentrations being equal to the equilibrium concentration, and the gradients of the carrier concentrations and potential are all 0 at non contacted boundaries. And we explained that in general the conditions, the boundary condition at the contacted or non contacted boundaries are derived in terms of the information about current at these boundaries. For example, at a non contacted boundary the net current either leaving the device or entering the device perpendicular to the surface is 0, okay. And similarly for contacted boundaries one can derive the boundary conditions based on information about the current density.
Sir, for the nanowire characteristics, can you give some reference for the measured and simulated data?
Yes, I think I should have provided the reference. Thank you for pointing that out. So, this data is now given here on the slide. So, the measured data has been picked up from a paper by Bauer et al. Published in Applied Physics Letters in 2007. You can do a Google search with this name and this year in Applied Physics Letters and you will get the reference. The simulation is our own, and this study was published, presented in a conference, International Workshop on Physics of Semiconductor Devices, conducted in IIT Kanpur in 2011. By presentation was by myself and my students, namely Vijay Kumar and Jayanand.